lives forever. Once again. So I don't have too much to say about it. Again, nothing has been proven about it. But it's a little surprising. I don't know whether this is, I mean, in a sense, the structure of the U sequence is more surprising because it has these kinds of patterns. By the way, I might point out just a sort of obvious similarity between the U sequence and the V sequence. The V sequence, as I pointed out, from the, let's say, terms 40 through 79, you can get terms 80 through 159 and so forth by just replacement. So it's as if there are generations, there's a generation of terms that produces a twice as long a generation, and then there's another twice as long, etc. So it seems as if there's a sort of a power of two structure going on, and that applies also to the U sequence. In other words, in the V sequence it was proven. In the U sequence it has not been proven, but it seems to have that same quality of powers of two lengths, doubling lengths of these sort of generations, or piece of the sausages, if you wish. But here there doesn't seem to be anything, at least not superficially, you don't see any kind of any structure that has that quality. Also, by the way, in this what we might call the Conway sequence, that also is the same fact. It's always it's a power of two kind of a thing. Each thing, each of those scallopy things is twice as long as the preceding one. So there seems to be a power of two kind of a law that pervades these things, but here there's no evidence of it, at least not on the surface. Now,
so how much are you offering for that one?
Well, since it's less interesting, I'll go down to half. 250. 250, how about that? You're going to make me a poor guy. All right. Now, this one has different initial conditions. Just 1, 2, 3, 4. The same recursion, but different initial conditions. And so, like that. You get back the sausages. Not the same sausages, but some kinds of sausages. And that's pretty surprising. Pretty strange. So it seems as if inside this rule, there still is this kind of doubling quality, but we don't understand anything about it. Okay. Don't ask me for another. Might be on some deal. Okay. But it does certainly suggest that among all these functions, there is a kind of a unity. There is something going on behind the scenes that we don't understand. Okay, this is the general question with those initial conditions. Instead of the initial conditions 1, 1, 1, 1, 1, then the initial conditions 1, 2, 3, 4, etc. up to S. Take this one, for example. 2, 3. Any thoughts as to what might happen?
No sausage.
What?
No sausage.
No sausage.
Sausage.
Well, rest in peace. It dies. It dies at 55. Here's a graph. Here's a graph of it. Did that go away? Yes. So here's a graph. It went too high up there. You can see it went too high, and it made the argument negative, which meant the function died. So rest in peace. To U sub 2, 3 is gone. It's a curious fact. Here is U sub 1, 6. Okay, it dies. This is a log plot. It dies at 23:55. It goes out a long way before dying, but it dies too. So, pretty curious behavior. Do we have a kind of a period kind of doubling thing here? I can't tell. I cannot tell. Doesn't seem apparent to the eye, at least, but it might be. I mean, this might be at about half of that. I don't know. Well, of course, half this is a log plot, so it doesn't.
You would have run them through a spectrum analyzer.
Could be. Could be. Who knows? Anyway, there we are with 1 comma 6, just to give you a sense of what these kinds of things can do. All right.
If you define to be 0 for negative values, you can keep going forever.
Yes, absolutely.
So you might explore what's going on after this?
Yes, you could certainly do that. You could certainly define it for negative arguments or 0 argument and negative arguments. You could certainly do that, and then the question is, what would be the most natural definition? Whether it be 1s everywhere or 0 or whatever. Yeah, but yeah, you could do that and see what that gave, and that's certainly a perfectly valid exploration. There's nothing wrong with it. It's just that it wasn't the original definition, and it's kind of interesting to ask yourself. So this is, I don't know if you can read it, but it says lifetimes, and I think it says, initial conditions 1, 1, 1. So if you give, this is a table, R and S are the 2 arguments. This is S here, 1, 2, 3, 4, and so forth. I'm sorry, the table isn't really very well constructed, but this is R and this is S, labeling the axes. And this is how long the function lasts before dying for the 2 parameters R and S. So that, for example, the original function, which is where R and S are 1 and 2, there, Greg put this is Greg's table, he put a question mark. I would have said infinity, but maybe he didn't have that symbol on his, in his typewriter. But in any case, or his keyboard, but in any case, it is strictly speaking not known that it goes, whether it goes on forever. On the other hand, this one is known. 1, 4, that's V, and that goes on forever. And we do know that. So that should be should say infinity. But for some reason, anyway, these are, and then 2, 4, we already saw that. That's what I call W, and that goes on forever. So we have 3 infinities here, and everything else.
So for 2, 4, it's provably infinity?
Yes. The 2, 4. No, not the 2, 4.
Yeah,
the 1, 4.
So that's the question mark is right.
Yeah,
The 1,
yeah.
4
2 of these question marks are correct, and this one is an infinity. Okay. So this is we've only shown this table for this above the diagonal because it's symmetrical, so it's the same information on the other side, so we didn't reproduce it. So what we did notice is that if you go out here, for example, it's kind of hovering at roughly a constant level, and then it sort of triples. And then it kind of jumps around at that level and starts increasing. And the same thing happens, well, you can't see it here, but it starts to, it triples. There is a place where it triples, roughly triples. Somewhere out here. I don't know where it is. It's somewhere out here. And then there's another place out here. And there's actually a recursive rule, a very precise recursive rule that tells exactly where this tripling takes place. This is a tripling, in other words, of the lifetime. In other words, these functions they die early and then they die late, so to speak. Not very late, but anyway, 3 times later, or anyway, it's very blurry because this is kind of a chaotic sequence here. But there's a very discrete and sudden jump in the lifetimes. And that exists on each line, and it happens at a very predictable place, an exactly predictable place. That, again, has not been proven. But there is an exact recursion rule, which is basically that you take the preceding number and you add some offset, and you double the preceding number, and you add the distance out, and then you add a certain offset, and that gives you the new one. And you double that one and add another standard offset, and that gives you the new one. So it's, again, doubling every time. So there's a lot of doubling going on here. But we don't understand this table very well, and that's been, in fact, I'll show you something about that. Let's go back here. Let's just look at the top 2 rows. This row here is not really a row because this is just the S value. So we're looking at this row here, 7, infinity, 165, infinity, 61, blah, 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 blah. This row and this row. We just want to see what those things look like. And as a function of s. So we're looking at r equals 1 and r equals 2, and s is variable. Okay. So here is a plot of the lifetimes. I hope I've stated this correctly. As you can see, this is the 1s. And it looks like it kind of consists of 1, 2, 3, sort of 4 bands. But they're very blurry bands. You can sort of see them here, here. And then this is 2s. And this also consists of sort of bands. Now, let's look inside this structure. I blow up some area here and show you what it looks like. This is 1s just by itself, and there's the area between, let's see, 19,500 and 21,500 just blown up, and you can sort of make out in this stellar, in this cosmic, well, whatever you want to call it, in the sky, sort of bands. You can sort of see them, although they become less clear when they're shown this way. They're clearer actually if you go back there, and you can see them much more clearly there. But there is definitely a kind of an order, but it's chaotic at the same time. What about the 2s? 2s looks like that if you blow it up a little bit more and change the scale of the y-axis so you can separate these things a little bit more. And it looks again like about four bands, but as you can see here, this band sort of breaks up into 2, and if you look carefully, you can see little dots along here which are sort of below. There's a lot of structure, so let's look at that in more detail. That's if you blow it up in really fine, to see it in a very, very fine way. So now you can see that this band breaks up into about 3 bands, but they're very kind of crazy looking. This one has this property. There's sort of 3 things here, but then they jump around, and then there sort of goes down, and then there's sort of 3 things, jump around, and 3 things. It's extremely chaotic, and yet extremely regular. It's very, very hard to understand where this mixture of order and chaos comes from.
And that's all conjectural.
This is just numerical.
Yeah.
This is all just numerical data. There's nothing conjectural here. It's just showing a graph. Yeah, there's not even a conjecture made. I suppose we could make a conjecture in a certain sense, but it would be a conjecture about certain things lying between certain bounds. That's about all you could say. It would not capture the order very well, because I don't know what conjecture to make that would capture the order more than just saying certain things lie within certain cones, and that there are certain sub-things, there are certain areas that are not allowed. Like you would say, there's nothing that happens in this blank area, where you can define that as being a kind of a cone. That's about all you could do as far as making conjectures go. You could invent a conjecture, but it wouldn't be as rich as the structure that you see. I mean, what kind of a conjecture could you make that would capture this kind of how could you what kind of conjecture can you make?
Well, it's reminiscent of chaos, the Feigenbaum style, and physicists have their own way of saying things. So maybe
I don't know. I really don't know how to characterize it. I mean, it's worthwhile thinking about it. Okay. Now for the 1, 2, 3, 4 family initial conditions, you can ask the same question. What's interesting here is that you have an infinite set of infinitely long living functions. And also here and here. there are two families that live forever. One of the form R, well, the indices of R and S are the indices where S is equal to 4R and where S is equal to 2R. And those are the two infinite families. In other words, if Q sub R comma 2R lives forever, Q sub R comma 4R lives forever. But all the others die. And again, if you look at this, now I don't remember if we found any evidence for any kind of cliff the way we did before, that is where there's roughly a tripling or something. Well, there's sort of a big jump. I don't know. I don't know. I don't know how much we've explored this. Anyway, so to show it to you graphically, it looks like that. This is just bad photocopying. The photocopier had some glitches in it. That's nothing to do with the function itself. What's very curious here, I must say, and I really find this mysterious, is that when you look at these kinds of plots, they're reminiscent of the plots of the functions themselves. Why is that? Why is it that the plots of the lifetimes of the functions, as a function of the index, this is the index where R is 2 and S is variant. Why is it that the lifetime of these recursive functions exhibits this kind of same structure as the function itself, roughly speaking? That's a very, very weird kind of question. I have no answer to that whatsoever. So this is just stating what I just stated. That in the 1, 2, 3, 4 family, we have the following immortals: 1, 2, and 1, 4, 2, 4, 2, 8, 3, 6, 3, 12, 4, 8, 4, 16, 5, 10, 5, 20, etc. And this would be, in general, that no matter what the initial conditions are, you name them, you choose any initial conditions, that the only time you will ever get an infinitely long-lived function is in this case. Again, just a hypothesis. I suppose I should put out some money on this one as well. And it'll be recorded, so I don't have to remember this. I'll say $200, please. $200. All right. Now, let's see. This is a picture of what I call the last gasp. That is, when a function dies, it gives you a negative argument. And since it has a negative argument, it can't, there is nothing to add, so it dies. So this is the negative argument as a function of S, where R equals 2. In other words, we're now exploring all of the family of functions of where the meta-Fibonacci functions where R is 2 and S is variable. When do they, not when do they die, but how do they die? What is their last gasp? What is the last thing that they say before going out of existence? And so the negative argument is shown here. And that's what it looks like. That's the negative argument. And again, similarly to the lifetimes, the negative arguments or the last gasps have this kind of band structure, and who knows how to analyze that. So that's one more bizarre thing. And I think I'm going to conclude a little early, to my own surprise, with one last thing that is a surprise to me. We explored, I don't know whether to hit the button or not, because I want to have it be a little surprise and I don't want to. We explored the initial conditions with, let's see, well, I don't remember what the R and S values are. They may be 1 and 2, or they may be 1 and 4. But in any case, I think they're 1 and 4. I'm not sure. Anyway, with the initial conditions of all things, 2, 2, 2, 2. Now, you might expect that to be boring and stupid, but in fact, that's what it looks like. 2, 2, 2, 2 with the initial conditions. Let's see, does it say here? It says, triple U. Okay, so that's with R equals 3 and S equals 6. 3 comma 6 with the initial conditions 2, 2, 2, 2, 2, 2, 2. And that's, it breaks up into these two cones, which we had never seen before. Right? We had seen something like that, but in a different kind of a domain altogether, that is, in the lifetime chart. But this is one of the functions. This isn't the chart of lifetimes. This is just a function, just one single function, 3 comma 6, with those indices, with initial values 2, 2, 2. And we get these kind of things. So it seems as if this domain is just absolutely filled to the brim with functions that seem to have totally chaotic behavior, and yet some regularity appears. In this case, two kinds of major cones that the eye can separate, but that mathematically it would be very hard to define. I mean, you could certainly talk about densities and things like that, and you could define it, but what I mean is it's a very blurry notion. It's not a clean kind of a notion. I might say also that Klaus Pinn has explored some other variations on these functions, and I don't remember the details, but he has an infinite family of functions, if I recall correctly, that as the parameters get larger and larger, have behavior. They're very chaotic, but as the parameters get larger and larger of the functions, there is some aspect of them, and I don't know what, he sort of subtracts off some value to make the functions, to reveal certain structures of the regularity of the function. He subtracts off like n over 2 or something like that. Anyway, when you do that with his family, his infinite family, you find that when one of the parameters increases, the family's behavior looks more and more and more like the Conway sequence. So in other words, it's as if it's chaotic, but it's getting less and less chaotic as the parameters grow larger and larger. It's getting more and more predictable, which is kind of another very strange aspect of it. So I think that's enough. I think that's all I have to say, and thank you very much.
Is the obvious generalization of the meta one uninteresting?
What is the obvious generalization?
F of n.
Oh, you mean 3
F of
times?
n plus, no. F of n plus 2 equals f of n minus 1 plus f of n minus 2. To me, that's the obvious one. Is that uninteresting?
I can't remember what that gives. I see what you mean. Instead of subtracting n
No, put the n minus in
yeah,
there.
I understand. Yeah, I can't honestly remember what that gives. I know I explored those kinds of things a long time ago, and if I were capable of doing arithmetic fast in my head, I could give you an instantaneous answer.
I'm not interested.
You know, but no, I remember exploring that. It's a very natural. You're right. It's the obvious. It's the more obvious meta Fibonacci. You're quite right. In case anybody didn't understand it, I'll just write it out. So you would say f of n equals just f of n minus 1 plus f of n minus 2. Yeah, no, that's a very good question. There's so many generalizations you could ask. What happens is you add 3 terms instead of 2 terms, and many, many other things. There are all sorts of generalizations one could make. And so I've explored, I explored a great deal. When I say I have explored them, that's a little bit inaccurate. I mean, it depends on whether you identify yourself with yourself now in the last few years, or if you speak of it in the past. I mean, I explored these things back in the 60s and 70s with quite some avidity, and then I stopped. So I think I would use the past tense. If I were still doing it now, I would say I have explored them. But the trouble is, it's sort of blurry as to whether I am still doing it now. I'm drawn to doing it, and I sort of do it for a little bit, and then I drop out, and so forth. So I don't know. In any case, whether it's the past tense or the present perfect, I don't know. But I know I some suitable tense attached to the verb explore. Many variations, and these are the most interesting ones that I've found. But other people have explored different ones. As I say, Klaus Pinn came up with a different set, and Steve Tanney and company have explored yet a different set. So it turns out that there are all sorts of variations out there.
Well, let's thanks back again.